Today we will see the Fredholm's first theorem and some examples how to solve the integral equation by using Fredholm's first theorem. So let me state the theorem. Fredholm's first theorem. I will state the theorem. Proof I will leave as exercise. Theorem. The non-homogeneous Fredholm integral equation non-homogeneous Fredholm integral equation of the second kind write the equation y of x is equals to fx plus lambda integral a to b. We are talking about the Fredholm integral equation. So plus lambda integral from a to b kernel k x comma t y of t dt. Let us take this as equation 1. Where our function fx and y of x are integrable as write down that as integrable as unique solution. That means your integral equation has unique solution. Given by y of x plus y of x equals fx plus lambda integral from a to b gamma x t lambda ft dt. And if you have noticed in previous methods we have seen this form where this gamma is called the resolvent kernel, right? So here where this gamma x t lambda, it's a function of x t and lambda, is a meromorphic function. This you need to check what is meromorphic function. It will come from functional analysis. First we define something called as analytic function, and this concept is extended, and you define something called as meromorphic functions by defining poles and singularities, all those kind of things, right? So check what is meromorphic function. When you call a function to be meromorphic function, and again you can read some theory of these meromorphic functions. So where gamma x t lambda is a meromorphic function of complex variable lambda. Now remember, when you say complex variable lambda, we are assuming that lambda is a complex number, and definitely if it is complex number it may be also a real number, so don't get confused out over there, right? So where gamma x t lambda is a meromorphic function of complex variable lambda given by let me write what is that, same as we have seen earlier. Gamma x t lambda is equals to d x t lambda upon d lambda, and of course you should not have your denominator 0, right? And here gamma x t lambda, that is your resolvent kernel, converges for all values of lambda. And again, since we have stated here what is dxt lambda and d lambda, let me write what is that dxt lambda and d lambda here in this Fredholm's plus theorem. So where this is very important, dxt lambda is equals to this. When you prove the theorem, you will come to know how you will get this. Your kernel kxt plus summation some p from 1 to infinity minus lambda raised to p divided by p factorial. Then you will have integral k. I will tell you what is this. X, the x1, x2 to xp, and t, again x1, x2 up to xp, and these are p integrals. So that will be, let me write here. This will go, if you take the PDF, it will go out. So let me write here down d x1, d x2, d xp. So here there are p integrals, and this I'll tell you what is this in the next few minutes. Let me take this as equation 1 here, say Roman 1, right? And then again we have to state what is this d lambda. So, and d lambda is equals to 1 plus summation p from 1 to infinity minus lambda raised to p divided by p factorial, and again here we have integrals k. Now as compared to this, we don't have x and t, because when you integrate this, all the variables will go. When you will have x comma t, again we have x comma t here, and so this d is a function of x, t, and lambda. But in this case, here there is no x and t, and again here we are not taking this x and t. So this is x1, x2, xp, x1, x2, xp, and then those integrals dx1 up to dxp. Let me tell you what is this. Let me write this as equation 2. Right? Now here remember, if p is equals to 1, you will have just x1, and hence you will have only one integral. If p is equals to 2, you will have two integrals. If p is equals to 10, you will have 10 integrals. Likewise again here, if p is equals to 1, you will have only one integral, that is k of x comma x and x here and dx1. If p is equals to say 3, you will have 3 integrals, right? So this proof I will leave as exercise. Try to prove this theorem. Okay. Now let me write some remarks from the proof I will get, and how you will get those k's in both the cases. Remark: so your k, this k is given by something like this. It's a determinant. So k of x, x1, xp, t, x1, xp. Now this is the determinant. You can guess what is the order after once I write this. K x comma t, right? K x comma x1, K x comma xp. So there are total 1, 2, 3 up to p. That means you will have p plus 1 columns, 1, 2, 3 up to p, and then plus 1, p plus 1. And for the this column you can write k, you fix this t as it is and vary this x to x1. So x1 t, k xp t. So again there are p plus 1 rows, and here you will have k x1 comma x1, k x1 comma xp, this is 1, this will be k xp comma x1, and last we will have k xp comma xp. So this k and this will be your determinant of order n plus p plus 1. And similarly your small this other k of x1, x2, xp in the in this expression here in 2 is given by again the determinant of order p plus not p plus 1, p given by same. You just don't take the first column here. So it is k x1 comma x1, k x1 comma x2, k x1 comma xp, then here k x2 x1, k x2 x2, k x2 xp, and the last row will be k xp x1, k xp x2, k xp, and this is how you will have this this first k in your first equation and the k in your second equation. Now equation 1, let me go on the next page. Equation 1, that is Roman, is called Fredholm first series and equation 2 is called Fredholm second series. So this equation 1 is called Fredholm's first series and this equation is called Fredholm's second series. And again those are determinants. So these determinants are called Fredholm's first and second series are called Fredholm determinants, right? And then third, the determinant or determinants in Fredholm first and second series are called Fredholm determinants. So these are also called as Fredholm's determinant. Now, if you denote this, you go for 4, denote is small c, small cp is equals to those integrals, p integrals k x1 xp x1 x2 up to xp dx1 dxp. So if you denote this integral as small cp, then your equation 2, this equation 2 will become d lambda plus 1 plus summation minus lambda raised to p upon p factorial, and this entire integrals you have denoted by cp. So it will be this summation, this term, and cp. Then equation 2 becomes d lambda is equals to 1 plus summation p from 1 to infinity minus lambda raised to p divided by p factorial cp, small cp. In coming time I'll use also capital C. So just distinguish it between C and the small c and capital C. And this summation starts from p is equals to 1. And what if p start from p is equals to 0? If p is equals to 0, then this is 0 factorial, this is raised to 0, and c0. So if you denote c0 by some number, we can start this series from summation p from 0 to infinity minus lambda raised to p divided by p factorial into small cp, where I can see with small c0 is equals to 1. So you start from, when you put p is equals to 0, this is raised to 1, numerator is 1 here, this is 1, and you will have c0. And if you denote that c0 by 1, that is your first term, and then your series will start from p is equals to 1. So if you denote this integral by small cp, our integral, this equation 2 becomes this series. Okay. Similarly, if you try to denote the other one in equation 1, let capital C0 of x comma t is equals to your kernel kxt, and you denote your capital CP of x comma t as your integrals in that equation. T, you start from x, so x, x1, xp, t, x1, xp, and then p integrals, so dx1 up to dxp. If you denote it by like this, then equation 1 becomes, then equation 1, don't write I, equation 1 becomes dxt lambda is equals to your kernel, so we have denoted your kernel to be c0, so c0 comma t plus summation t from 1 to infinity minus lambda raised to p upon p factorial, and here we'll have cp of x comma t, and this is from your equation 1. So in this equation, this you are denoting by c0, the summations are there, and this integrals you are denoting by cp. So this entire equation becomes the way we have written here, c0 of x comma t and this. Now there is a relation between this capital C's and small c's. So that recurrence relation I will give you, you try to prove, and in some of the problems we can use that recurrence relation as well as this determinants. So let me write that as 0.6. This capital CP, and of course x comma t is there, and the small c cp, remember these are the constants now, satisfies the following recurrence relation. Your small cp is equals to integral from a to b, whatever limits you have, is capital C c minus 1 x comma. Now remember you have only one integral here, and the cp is a constant. So cp minus 1 of x comma x dx, and your capital cp goes x comma t is there, is equal to small cp into capital C0 x comma t minus p integral from a to b p of x comma u dp minus 1 of u comma t du. So if you have the values of this cp, small cp and capital cp, you can easily find what is dx d lambda and d lambda by using this series. And if you have dx d lambda and d lambda, you can find the resolvable kernel, which is given by this. And once you have this, you have the solution of your given integral equation. Right? So when you are solving any integral equation by using this theorem, you can use this things to find your kernels, and then integrate, and then dx d lambda and d lambda, and hence your resultant kernel. Okay? And second thing to say here is we have the value of c0. Okay? So in order to find c1, we have to find the value of capital C0, and this is already given by using your kernel. So you can find C1, small c1. To find the capital C1, you need small c1, and that's what you have found already. And the small c0 you have, kernel you have, c0 you have. So the sequence, if you want to find those, find the solvable kernel by using this recurrence relation, first you should find what is c1. By using c1 and c0, you have to find capital C1. By using this capital C1, you can find C2, small c2, which involves capital C1. By using that small c2, you have to find C3, capital C2, and then so on. Okay. Let us take one example based on this. See. Example, not integrate all together. Y of x is equals to plus t y of t dt. Let us solve this by using your Fredholm's first theorem. Here, the kernel k x comma t is nothing but sine of x comma t, and then we are denoting this by your capital C0, that is C0 x comma t, and we already know what is C capital small c0, we have this as 1, and by recurrence relation we have this c1 small c1 as integral right 0 to 2 pi, and this capital formula is by using this recurrence relations we will answer with the opposites integral from e to b c e minus 1 of x comma x dx, and your capital C I can use it from your so your small c1 in this case becomes integral from 0 to 2 pi c0 of x comma x dx, and we have c0 of x comma t as sin of x comma dx plus t, and of x plus t, so this becomes integral 0 to 2 pi sin of x plus x dx. This becomes integral 0 to 2 pi sin of 2x dx, and when you evaluate this integral you will get 0. So your c1 is 0, and to find capital c1 we are using small c1. So in your case your capital c1 of x comma t will become c0 and c1, then capital c0 of x comma t, this we know what is that, minus p, now in our case p is equals to 1, minus p, that one directly, 1 integral 0 to 2 pi k of x comma u, then capital C of 1 minus 1, that is p minus 1, so in this case 1 minus 1 u comma t du. C0, sorry, C1 is 0, so first will be 0 minus integral 1 is there, so integral 0 to 2 pi sin of x plus u into your C1 minus 1 is 0, so C0 is again sin of u plus t dv. Now use your method of integrations, techniques of integrations, formulas which you have. When you evaluate this, that is right here. When you evaluate this, you will have minus pi cos of x minus t. That is your capital C1. By using capital C1, you can find small c2, and that small c2 depends on capital C1 that we have seen previously. So small c2 will become integral from 0 to 2 pi capital C1 x comma x dx. This becomes integral 0 to 2 pi sin of x comma C1 of x comma x. So this is minus pi cos of x minus x. Cos of x minus x is cos 0 is 1, so minus pi. So this becomes minus pi pi into 2 pi, and that is minus 2 pi square. Again, by using this small c2, you are finding capital C2. You find the value of capital C2 of x comma t by using the formula. You may write your answer 0. That we have verified. Find the values. And if capital C2 is 0, to find the small value of small c2, you are using that capital C2 as the integral, and then it becomes 0. And when both are 0, your capital C3 will become again 0, and so on. So in that case, your d lambda becomes hence thus the formula for d lambda we have summation t from 0 to infinity minus lambda is to p divided by p factorial into this small c3 is what we have found. This is c0 minus lambda by 1 factorial into c1 plus lambda square by 2 factorial into c2, and then rest all c3 c4 all are 0. Okay? And this is becomes c0 is 1, then c1 was 0, and then plus minus c2. c2 is minus, so it becomes minus lambda square by square 2 cancels out. So this is your d lambda, and then you have to find dx d lambda. Your x comma d comma lambda is equals to, this is the formula for that series, plus summation t from 1 to infinity minus lambda is to p divided by p factorial cp of x comma t. And c0 we know what is that, is kernel k x comma t, and for this capital space c1 is there, but c2 c3 rest all are zeros, so only one term will survive as summation, that is minus lambda upon 1, that is 1 factorial, and c1 x comma, and when you substitute the values you will have sine of x plus t plus c1 what is it, minus 5 cos of x minus t. So signs will change, it's lambda pi cos of x minus t. Once we have this d lambda and dx d lambda, you can easily get the resolvent kernel. The resolvent kernel gamma x t lambda, resolvent kernel gamma x t lambda is given by gamma x t lambda is equals to d x t lambda divided by d lambda, and then just now we have found the values of dx t lambda and d lambda. So dx t lambda was sine of x plus t plus lambda pi into cos of x minus t whole divided by your d lambda, and in our case our d lambda was 1 minus lambda square pi square, that was our d lambda. Right? So once we have this resolvent kernel by Fredholm's theorem, we know that hence the solution is given by y of x is equals to fx. If you have noticed, nowhere we have used this term in the calculation of this dx t lambda and d lambda, but in the proof you can check what is the significance of this fx? Right? So y of x is equals to fx plus lambda integral from a to b, that is 0 to 2 pi. Then you have the kernel x t lambda, and here f t dt. This is your solution for the given integral equation. In the next step, you can put this gamma x lambda as this function, and then that is your precisely the solution. Let me give some exercise. Exercise. Find the resolver kernel. Find the resolver kernel using Fredholm's first theorem. Let me directly give you what is the kernel and the values of a and b. So k x comma t is equals to 1 minus t xt of a and b of is random. This is not intervals, you can say the values of a and b. You can consider the intervals, no problem. Second, the kernel kxt is x minus 2t k x comma t is equals to a raised to x minus t. In this case, the values of a and b are 0, 1, and again in this case the values are from 0 and try to get the solutions. In the next we will see how to solve by using